this video, we're doing a repeat of my lecture on motion along a curve, motion in space. Just in case you missed it, this video might be a little bit longer. But we're going to imagine that this red curve in our picture starting here is your path through space, the final frontier. You are going boldly where no one has gone before. Yes, Star Trek. So this is trying to connect limits and derivatives with 3 space. So what we have here is we have some given point on our curve, and then we have a second point some distance away from that, and we have a vector connecting the two. Well, so we have basically the slope of a secant line, which is an average rate of change. But what we want to know is what's going on at this single point, so we want the slope of the tangent line. Well, like in 2 space and like in Calc AB in the definition of the derivative, the distance away from the 2 points is h. So if we use the difference quotient, we get r of t plus h minus r of t over h. If we take the limit of that as h approaches 0, which if I bring this up so we can see it a little better, then this would be the definition of the derivative, and since r of t is position, this would be velocity. So that's the theory behind things. Now what we know before from Calc AB is that speed is the absolute value of velocity. What we are learning now is with vectors, speed is the magnitude of the velocity vector. Now that's a key FRQ component in AP. Also realize that acceleration is still the derivative of velocity, or the second derivative of position. Seems logical to me. Example 1. So let's not take too big a look at that. In example 1, the position vector of an object moving in plane is given by r of t is t cubed I plus t squared j. We want to find its velocity, speed, and acceleration when t is 1. Well, velocity would be the derivative of position. Speed is the absolute value of velocity, or the magnitude, and acceleration is the second derivative. So if we find velocity, our first derivative, we get 3t squared I plus 2tj. Acceleration, the second derivative, would be 6ti plus 2j. Notice the I and the j stay in their normal positions. Speed being the absolute value of velocity, and that being the magnitude of our vector, we would take our terms for 3t squared and 2t in velocity. We would square them in square root and get 9t to the 4th plus 4t squared. So now what happens when we plug in a 1 to get our speed? Well, if we plug in a 1, we're going to get 3i plus 2j for our velocity. Our acceleration is going to be 6i plus 2j, and our speed, when we plug in, is going to be 9 plus 4 is square root of 13. So again, plugging in a 1 in our velocity, we get 3 and 2 as our coefficients, 3i plus 2j. When we plug in a 1 into our acceleration, we get 6 and 2 for our acceleration. In this example, we find the velocity, acceleration, and speed of a particle with position vector r of t, t squared, e to the t, t e to the t. Now let's keep in mind that back here, that's going to be product rule, so keep in mind that. So we're going to start with our velocity. Derivative of t squared is 2t. Derivative of e to the t is e to the t. And if we do product rule, we get first derivative of the second plus the second times the derivative of the first. We could then factor out an e to the t and get t plus 1 e to the t. Acceleration, or the second derivative, so now we've got the derivative of 2t is t, the derivative of e to the t is still e to the t. Now, once again, we're doing product rule, and we would get 2 plus t e to the t. Speed, again, is the magnitude of velocity, so if we take our 2t and square it, our e to the t and square it, our t plus 1 e to the t and square it, that's going to give us the square root of 4t squared plus e to the 2t plus t plus 1 squared e to the 2t. In example 3, a moving particle starts at the initial position r of 0 is 1, 0, 0 with initial velocity v sub 0 of I minus j plus k. Acceleration is 4ti plus 6tj plus k. Find its velocity and position at time t is 0. Well, so since velocity is the same as integrating acceleration, then let's go ahead and integrate acceleration. So 4t becomes 2t squared I, 6t becomes 3t squared j, k becomes, had a little visitor there, let's keep going. So if we integrate just 1k, we get tk plus c. Now, we can go ahead and solve for c because they gave us some information. They gave us that v of 0 is I minus j plus k, so we can go ahead and solve for c. So notice we plug in our I minus j plus k, and then on the other side, every time we see a t, we plug in a 0. Solving for c, we get I minus j plus k equals c. So our velocity function is 2t squared plus 1i plus 3t squared minus 1j plus t plus 1 k. McCoy seems to think he's not an engineer or a mathematician in either universe. Let's keep going with this problem. So now that we have our velocity function, what about position? Well, so Uhura believes our position should be integrating velocity. So here we are plugging in and we're integrating. Now we already used c. So once we integrate all three terms to get 2/3 t cubed plus t, t cubed minus t, and 1/2 t squared plus t, let's use plus d instead. I suppose you could use plus c, but we're just trying to be creative here. Again, we know that r of 0 is 1, 0, 0. So we would do the same thing. We would plug in the 1, 0, 0 here, zeros for t everywhere else. We then get d as being just I. Combine that all together. R of t is 2/3 t cubed plus t plus 1i plus t cubed minus tj plus 1/2 t squared plus tk. Uhura is certainly happy everywhere.